The night sky has fascinated humanity across the globe since ages. Counting stars on a clear night sky is a favorite pastime for kids across generations. The need for counting also spanned multiple numeric systems across different cultures, which were all understandably based in because of the 10 fingers on our hands. Correspondence principle can be applied while counting them using fingers. Surprisingly, this simple principle can also be applied while determining the size of infinite sets. Let's talk about finite sets. Okay, so for finite sets like these, you can simply compute their size and say confidently that one set is larger than the other. But if we try to count the elements in infinite sets, we will never be able to finish. George Cantor, a famous mathematician in late 1800s, was concerned about measuring sizes of infinite sets. He observed that two finite sets have the same size if the elements of one set can be paired with the elements of the other set. This technique bypasses the process of counting and the knowledge of a number system. So all you have to do is pick one element from one set and see if it has a corresponding element in the other set. Correspondence is basically a bijective function between two sets. Let n be the set of natural numbers and e be the set of even numbers. You might think that the size of e should be half the size of n, but you're mistaken. They are of the same size. To understand this counterintuitive statement, let us try out the Cantor's technique of correspondence on these two infinite sets. You could see that every number in the set of natural numbers has a corresponding number in the set of even numbers. Okay, so now is the time to formally define what it means when we say a set is countable. A set is countable if either it is finite or it has the same size as natural numbers set. Now let us see if the set of rational numbers is the same size as natural numbers. At first glance, it might appear that the set of rational numbers is bigger, but trust the correspondence tool provided by Cantor with this before coming to any conclusion. First, let me visualize the set of rational numbers this way. A rational number is a fraction with numerator and denominators which are natural numbers. If you observe closely, there are few duplicate numbers here. We can ignore them. Now let us start to identify unique rational numbers and do a correspondence with natural numbers. There you go. Starting with 1 by 1, 2 by 1, 1 by 2, 3 by 1, and so on and so forth, I'm able to sweep through all the rational numbers in order and do correspondence with the set of natural numbers. Hence, rational numbers are countably infinite and have the same size as natural numbers. It seems like any infinite set whose elements can be written in certain order are countable. What about the set of real numbers? Between a pair of natural numbers, there are infinite real numbers. Real numbers constitute of numbers that are not rational, like pi or root 2, which have an endless stream of numbers after the decimal point. Cantor proved real numbers are uncountable. To prove this, we will use the technique of proof by contradiction. First, we start by assuming that real numbers are countable and a correspondence exists between natural numbers and real numbers. Let us consider the set of infinite real numbers between 0 and 1. I'm picking a few numbers and listing them in this table. Now, what I'm going to do is focus on the diagonal. I will create this new number x in such a way that the digits in x are anything different than the number we have in the diagonal for that particular digit. I can keep doing this for every number in the infinite set. So clearly, this number x cannot be in the f of n because it differs from every element in f of n at the diagonal. This is a contradiction because the number x should clearly be in the set of real numbers between 0 and 1, yet, our way of constructing this shows that it can't be. Hence, our assumption that a correspondence exists between natural numbers and real numbers is false. Not all infinite sets have same size. Real numbers are proven to be uncountable using Cantor's diagonalization technique. We will see diagonalization in action several times in the course. Go back and forth in the video segment that talks about diagonalization, and if it does not make sense to you, reach out to me. I'll give you more insight to it.